All right. So today we're going to actually go into chapter 3. Now remember the homework for chapter 2. If you can have it to me by Thursday, that would be good. And just send it by email. You just email it to me. There's only the fifth person in the course couldn't continue with the course. She's not doing well with health, and so she had to leave, unfortunately. And then the other person in our group, the 4, she'll be back on Thursday, so she has some work that she has to do. So it's us 4. We're all going to be meeting at the same time now, so make it a little easier. All right. So chapter 3. So chapter 2 is all about graphs, and chapter 3 is about some summary, what we call summary statistics. All right, and this is something, of course, what you were just showing me. You were showing me some summary statistics, but we're going to get into the really basic ones now. You can see the screen here, right? I'm going to click Enable Editing. There we go. Oops. I don't know why it does that, but let's do it again. All right, so this should work now. So there we go. All right, so statistical description of data. So we're going to focus on one type of summary statistic, which is called central tendency. In other words, it's a number that summarizes all the other numbers in the data, all the numbers in the data set. All right, so you've all heard of the mean, the median, the mode. And that's what really the type of thing we'll look at today, and a couple of other ones too. Then on Thursday, we'll talk about the spread of the data. And that'll be the next topic after that. All right. So this is sort of the learning objectives for the entire chapter. It's including things that we may not cover, which is like the correlation coefficient. We're not going to cover that till the end of the course. So we'll come back to this topic at the end of the course. But the other things that are here, we're going to be looking at. And then we'll look at the mean. Now, just for your information, Greek letters are used for population, what we call parameters. So we use the word parameter to refer to the summary statistics for a population, and we use Greek letters for them. We use English letters with maybe some notation with it to represent sample statistics. We call them statistics when it's in reference to a sample. Okay, so for example, for the mean, we use mu, the Greek letter mu, for the population, and we use x, what we call x bar, with a bar on top of the x, to represent the sample mean. So population mean is mu, sample mean is x bar. All right, so just get used to the terminology. There isn't any letters that necessarily represent the weighted mean. This is something we'll talk about in a minute, the weighted mean. And nothing in particular is used for the median or the mode, so typically you just write out those words. All right, so the center of the distribution of numbers in your data set, these are examples of them. All right, it could be others, but these are the ones that we're going to focus on. And then on Thursday, we're going to talk about measures of dispersion or spread, how spread out the data is. And we'll talk about things like the range, the mean absolute deviation, not used very much, but we'll define that. The variance is used a lot, and we'll have notation for that. And then derived from the variance is the standard deviation. Something that you may not have heard of before, the interquartile range. We're going to talk about that once we talk about quartiles. We'll talk about what this interquartile range is. And coefficient of variation is another measure that we'll mention. And then the third part of this chapter deals with measures of relative position in the data set. We'll talk about quartiles, deciles, percentiles, things like that. And then these here, we'll talk about again towards the end of the course. When we talk about linear regression, we'll mention coefficient of correlation. We may talk a little bit about coefficient of determination, what that means. All right, so that's sort of a summary of this chapter. Again, some of it will be for later, and most of it we'll cover in the next 3 meetings. So the center is the mean. One of the measures of center is the mean. The mean is very easy to calculate. You basically sum up all of the values in the data set and divide by the number of values. And it's true whether it's the population or whether it's a sample. Now, the formula for the population mean is this. Mu is equal to, and this symbol here, you've probably seen this symbol. This is the big letter sigma in Greek, which means sum, all right? We sum up. So we're summing up the values in a data set, and we're dividing by, for the population, we use big N to represent the number of values in the population. Similar formula for the sample mean, X bar is equal to the sum of, again, the values in a data set divided by small n, which is the number of values in the data set for the sample. We use small n for a sample count, and we use big N for the population count. All right, does that make sense? Okay. All right, so this is an example here. Calculate the average number of truck shipments from the United States to 5 Canadian cities for the following day data given in thousands of bags. Okay. So Montreal has a number, this is 64 thousands of bags, and Ottawa 15,000 bags, like that. And so there's how many numbers? There's 5 numbers. You just add up these 5 numbers and divide by 5, and you get 127.4. All right? So that's called the arithmetic average, or simply the mean. All right, so the mean and arithmetic average means the same thing. Simply add up all the numbers and divide by the number of numbers. Any questions about that? Pretty straightforward. I think everybody knows this from even grade school, right? All right, now there's a special one called the weighted mean. Now, if we go back to the mean, what's the big assumption that we're using here? We're making the assumption that each of these 5 values here are equally weighted, equally weighted. That means they're just as important as, each one of these is just as important as any of the other values here, right? We're not putting any importance on any of them. So we call that equal weighting, the arithmetic average, right? So we don't even have to bother with weights. We simply divide by the number of values, all right? But if we wanted to weight these values by something else, okay, then we use this formula called a weighted mean, all right? So when you have what are called grouped data in groups, okay, these would be groups, right? Montreal, Ottawa, Toronto, Vancouver, Winnipeg. And you want to weight them unequally, then what you do is you multiply each weight by the value, then add up all those products, that's your numerator, and the denominator is you're adding up all the weights, all right? And when you do this calculation, you come up with the weighted mean. Now they use mu here, but that would be a little misleading because mu is the symbol for the arithmetic mean, which is unweighted, all right? So I wouldn't use this symbol here. I would probably use some other symbol to show weighted mean. Anyway, what are they doing here? They say calculate the average profit from truck shipments. So this is a little bit of a different question, right? The average profit from truck shipments U.S. to Canada for the following data given in thousands of bags and profits per 1,000 bags. All right. So what you're doing is you're multiplying the number of bags in thousands by the profits per 1,000 bags, right? And that should give you total profits. Now this is considered to be a weighted average because what you're doing in this sense, I mean, it's a little misleading because they say average profit, right? Well, it's really a weighting because you're taking your profit per 1,000 bags, right? And you're multiplying by the weight. Weight in this case is what? The number of thousands of bags, right? Yeah. So you're multiplying these two numbers, the weight being 64, 15, 285, 228, and 45. Those are the weights. So you multiply the weight times the dollar amount, which is X in this formula. So you multiply these two numbers, these two numbers, these two numbers, these two numbers, and these two numbers. And then you add up the weights for the denominators. So what are you adding up? You're adding up 64 plus 15 is 79. And then you add that to this number, 79. So that's 364, right? And then this is another number here, 364. So that's 592. 592 plus 45, 592, 637, I believe. And when you add up all the weights, so you multiply these products, divide by that sum of the weights, and you should get $14.04 as your weighted mean. Okay? Now in this particular case, they say average profit, but remember the profits in total dollars here, right? Or no, it's actually per 1,000 bags. So this is sort of a weighted average. So they really should say weighted average here. So otherwise, if it was just average, simply an arithmetic average, right? You would simply add these $5 amounts and divide by 5, wouldn't you? Right? It was a simple arithmetic average of these profits per 1,000 bags. You would simply add it up to 5 and divide by 5, and you get some other number. But we're using weights here, okay? These weights will change, will give you a different answer. So what we're basically saying in this case here is that Toronto's profit is given the most weight because it has the most bags, right? 285, so this Toronto is the biggest weight. Vancouver is the second biggest weight. Montreal, the third biggest weight, right? Then Winnipeg, and then Ottawa has the smallest weight. So that's going to change the dollar amount, all right? That's going to change it from 1404 to some other number. Excuse me, it would change the arithmetic mean to 1404. 1404 is the result of that. This is the weighted mean, and the arithmetic mean, you just added up those 5 numbers, would be something else, probably something smaller, right? And the only reason I'm saying smaller is because the biggest weight is on the biggest price, the profit number here, isn't it? Yeah. So good chance that this number is bigger than the arithmetic mean. All right. Any questions about weighted means? All right. Another example of weighted mean would be your grade in this course. All right. I have different percentages for different parts of the course, right? I have what is it? Quizzes. I have projects. I have tests. I have a final exam, right? They all have different weights. So each of those will have grades assigned to them, numbers assigned to them, and then you would multiply each of those weights by the grade, add them up, and divide by the sum of the weights. Now, in the case of of a grading scheme, like for a course, the sum of the weights are going to be equal to 1. All right? So in that case, you're just basically multiplying the weight times the grade, and you add them up, you get your overall grade, because you're dividing by 1. In this case here, you're not dividing by 1. This is the sum of the weights here. It's a big number. All right. Any questions? Weighted mean? All right. Median. Median requires that you put the data set in numerical order from smallest to largest. All right. That's what they mean by an array here, that you're putting it into an ordered array. And here's the deal. It's pretty easy to find the median. If you have an odd number of values, of numbers in your data set, then the median is the one in the middle. How do you find the one in the middle? Well, it's not so hard to do if you have a small data set, but what if you have a larger data set? What if you have 1,021 numbers in your data set? What position is the one in the middle? So how do you find it? Well, the simple formula, you might be familiar with this, is you take the number of values in your data set, add 1, and then divide by 2. And that gives you the position of the middle value. All right? So that's how you find it. So if you took 1,021, added 1, which is 1,022, and divide by 2, you get 511. 511th position in the data set is going to be your median. All right? That value. If you have an even number of numbers in your data set, then it's the average of the 2 middle values after you've ordered the numbers from smallest to largest. And it's possible that that average of the 2 middle values is not a number in the data set. So the median is possible to be something other than a value in your data set if it's an even number of numbers in your data set. And use that sort of that formula I just gave you. You take, let's assume there is 50 numbers in your data set. So you take your 50, add 1, divide by 2, right? You get 25.5. And that means the 25th and the 26th positions. The 25.5 says 25th and 26th positions. Those two numbers, you average those, and that's your median. However, calculators, the graphing calculator software, it does the work for you. So you don't have to order it and do this manually. But if you had to, that's how you come up with your median. Pretty easy to do. Now, why do we want a median? If we have the mean, why even bother with the median, right? Well, the median sometimes comes in handy if there are unusually small or unusually large values in your data set. These are what we call outliers. It mentions it right here, word outliers. And what the outliers might tend to do, it might tend to skew the distribution, making the distribution have unusually large or unusually small values. In that case, the median may be a better measure of the center of the distribution of numbers in your data set than the mean. And we'll look at examples in a couple of minutes, okay? So it'll be clear what we mean by that. The mode is the most frequent value in your data set. So you just go into your data set. Now, let's say that the data set, you look at all the values in your data set, and there's no repeats. Every number's unique. Then there's no mode, okay? Then you would say no mode. There's only one value for each, one repetition. But if you have repetitions, you have repeats, then the one that is repeated the most is the mode. And if you have more than one that's repeated the most, then you have a tie. And then you could say there could be 2 modes or 3 modes like that, all right? And they're all repeated the most. Now, the mode is not used as much. However, it is used in describing the shape of a distribution. For example, if you have the so-called bell-shaped curve, all right, where its tails off to the left and right, but it has this bell in the middle, that's considered one mode. Unimodal, that's a word that we can use, unimodal, U-N-I-M-O-D-A-L. But sometimes numbers may have bimodal. There might be two modes. You might have two bumps in the data. And sometimes the reason for that is that we may have in the data two groups. Maybe they weren't described as groups, but the data is indicating there might be two groups or three groups, whatever. And that's where the mode comes in. It gives you an idea of grouping. There might be some grouping going on. Okay, that's the mode. Now here's the deal, here's the big thing. It's in your book. I would recommend that you read chapter 3 so you get used to these terms. If and in your book, it shows examples like this. If the mean is equal to the median is equal to the mode. Now, when we say equal, in most cases, approximately equal, all right? Data is messy. It's never exactly equal. But if it's pretty close to being equal to each other, then we could say this is a symmetric distribution. Bell-shaped curves is an example. We could have data that where every number in the data set's the same number, right? Uniform, it's called. That's also where the mean, median, mode are also the same. Now, if there is a significant difference between the mean, median, mode, then we say that the distribution is skewed. Skewed means non-symmetric. That's what it means. If, and here's the big thing here. If the mean is significantly bigger than the median, and the median is bigger than the mode, this is called positively skewed. This is a case where you may have unusually large values in your data set. And what happens is that the mean is pulling, because of these large values, the mean is being affected by these large values. Let me give you a silly example. Suppose there are 4 people or 5 people, let's say 5 people in a McDonald's restaurant. And you walk around, so you're doing a little survey, and you're asking how much these people make per year. And let's say they all make around the same, somewhere between 40 and 60,000 maybe per year, something like that. What if one person walks out and Warren Buffett walks in? Now, Warren Buffett is known to love McDonald's. He's owned it for years as a stock, and he loves it. He eats it there all the time. And so, and then you don't recognize Warren Buffett, so you go up to him and say, "Sir, I'm doing a survey of people's income. How much did you make last year in income?" And he says, "Oh, I think I made about $6 billion." All right, so everybody else is making 40 to 60,000 per year, and he makes 6 billion. Now, if he was the 5th person in the data set, right, if you ordered it from 1 to 5, right, the mean has been changed significantly, right? The mean is now, in billions instead of in thousands of dollars. But the question is, did the median change? The person walked out and let's say he or she was making 50,000 a year, and Warren Buffett walks in, he's making $6 billion per year in earnings. Did the median change? Well, if that person who walked out had the largest income, and he was replaced by Warren Buffett, who's again the largest income, the median hasn't changed. The median stays the same. The third person that's the median is still in McDonald's restaurant, but the mean is much bigger. So this is an example of an outlier. Warren Buffett's the outlier, and he's pulled the mean to a significantly greater value than the median. So let me see if they have any shapes here. They don't have the shapes in this here, but it's in the book. If you have your book there, I guess we can even show you examples. On page 63 in your book, they show you the pictures of the skewness. This is a case of positive skewness, positively skewed. And what it looks like the bump of the distributions to the left, and then it tails to the right, tails down to the right. Well, some people get this confused. They think this means negatively skewed, but it is positively skewed because the tail is moving towards the right. Think of it that way, moving in the positive direction. The money in general is an example of positive skewness, right? Because money goes down to zero, and then you can have an unlimited number of amount of money going to the right. Yeah. Then we have what's called negatively skewed. That's when we have unusually small values. That's making the mean smaller than the median. All right. So you can picture again the five people in the restaurant, and maybe the person with the smallest income leaves, and then somebody walks in and only has $10 to their name, and they're going to spend it on their last $10 on a McDonald's meal, right? So $10, they don't have any income coming in. That's all they have. Everybody else has thousands of dollars in income. So that's going to pull the mean lower, much lower than what it was before. A outlier that's very small, that person who doesn't have much money. And that's called negatively skewed. Why do they call it negative? Because it's pulling the mean in the negative direction towards zero. And the way that shape looks is that the hill of the distribution is towards the right, but the tail's moving towards the left. That's called negatively skewed. Other words that they use for this, by the way, the positively skewed is also called right skewed, which means the tail's moving to the right. And negatively skewed is also called left skewed because the tail's moving to the left. All right? But people tend to get those backwards. Now, for negatively skewed, the mean is going to be smaller than the median, and the mode, again, will be bigger than the median. So the mode's going to be the biggest of the three, typically, and then negatively skewed. And the mean is going to be the smallest, with the median in the middle. And then positively skewed, the mode is going to be the smallest, okay, with the mean being the biggest, and then again the median's in the middle. All right, so there's a relationship between mean, median, mode, approximately equal for symmetric, and for the two skewed, they are significantly different from each other. And you just have to, this slide here, you have to sort of memorize it, unless intuitively it makes sense to you and you can figure it out, okay? This slide's important. All right, and that is it for what we're covering today, but I do want to go over some Minitab examples with you, all right? So we're going to spend the rest of the period, for the next 20 minutes, 25 minutes, going over these examples. All right, so let's get out of this and get to Minitab. All right, and I'm going to close this out. This is the one that we were just showing before. I'll close this. Actually, there isn't a close button here, so I think I'm just going to say open, and maybe it'll allow me to open up another one here. Give it a shot. And I have one called September 22. That's the project that was. Save changes to this. Did we make any changes to this? I don't think we made any changes, right?
No.
No, so I don't think there was any changes. All right. And I just realized I spelled solutions wrong here, so I'll go ahead and change that. There we go. All right, now the first tab here is on page, it's basically the section example, 3.1, says computer solutions on page 65. This is a familiar data set. This is the ATM data set that we saw last time. For some reason, they decided to go back to chapter 2 and use this data set. You do have this. This is the ATM one. So if you wanted to go back and open this up again, again, this is what it looks like. It has an age category, gender, and also ATM time in seconds. All right, now in this case here, now they tell you in the book to just simply come up with a descriptive statistics for this data set for the seconds here. And what I did was, and you have the option of doing this too, I ended up unchecking some boxes for things that are not yet learned, because it had things, it defaulted to things like variance and standard deviation and things that we're going to learn in the next 2 meetings. So this one, I just unchecked it. So I went into stat, basic statistics, displays descriptive statistics, and so basically for this one here, this looks like something else. All right, I don't understand what this is here, so I'll get rid of it. So what I did was basically took seconds, right? And then if you click statistics here, I believe for the Mac has the same button there for statistics. You have all these options. It's true, right? You have that? Yeah. So I just unchecked some of the things that were there by default. All right. If I wanted to do all of them, all the default ones, I would click all here. But I just checked the mean, the median, and the mode. I don't have it checked, but I will check it. And I also, there's something called the trimmed mean. Now, we didn't go over that, the trimmed mean. But that's not something that's very important. What a trimmed mean means is that if you order the data set from smallest to largest, you can trim or remove the smallest and largest values in the data set by a certain percentage. So if you have like a 5% trimmed mean, then you might be removing 5% on the left, 5% of the data points on the left, 5% on the right. All right. Don't worry about calculating it. You can just click the box here and it'll give you the trim mean. But it defaults to 5% on each side. I unchecked the minimum and maximum. Didn't think it was necessary to do that. Skewness, however, I wanted to check that because we were talking about skewness, right? And skewness is an actual numerical calculation. All right. If it's positively skewed, it's going to be a positive number for skewness. If it's negatively skewed, it'll be a negative number. Okay. So and then I clicked OK, and I ended up with this here. And also, and notice it gives me all these modes here. Notice it. 26.3, 37.7, 37.8, 43.6. And now, I know you guys don't have this ability to highlight values like I do, right?
Right.
Right. But let's go back. But as you can see here, there are two 37.8s. There's two 26.3s. And if you do the other two, you would find two of them. That's where the green comes in, and yeah. So I know you guys can't do that, but I just wanted to show you that that there are two. There's a tie here for those four values. Each of these are repeated twice. So these are the mode. There's no number in the data sets repeated 3 times. All right, and it even tells you here, n for the mode is 2. So it actually counts it for you, which is nice. All right. Here, look here, gives you a positive skewness. And if you compare the mean to median, the mean is significantly bigger than the median, isn't it? The mean is 39.76. The median is 37.8. And we see positive skewness here. All right. So what's the shape going to look like? The bump will be towards the left, and then it'll tail off to the right like that. It's right skewed. It's positively skewed. Okay. So I wanted to show that to you. Any questions about that? Pretty straightforward, right? Nothing in particular here. By the way, in Minitab, the n represents the number of values in a data set. N star is the number of missing values. All right. So if there were any values that were missing, it would show up here. Anybody have any questions about this? I think it's pretty easy. All right. Now, in your book, for this section, 3.2, section 3.2, there's a couple problems I wanted to take a look at. 3.6 is, this is where they did not give you a data set to enter. So these are the closing prices held by an institutional investor. This is a case here where you would actually manually enter this data. So I put closing price as the title, and I just enter these 15 numbers here. Show it to you. 15 closing prices. All right. There's no data set here. You know, if I give you an exam or a quiz, I might ask you to use Minitab and simply enter the data instead of importing it. All right. And so what did I do here? Oh, one thing I forgot with the previous one. Let's just go back to the previous one. I forgot about this. The previous example, you could also find the mean and the median for groups, right? The different genders, gender 1 and gender 2. Forgot to mention that. And gender 1 is male, gender 2 is female. So when you go to stat, you have by variable here. So what would you use here? You would use, the variable would be seconds, and the by variable would be gender. So you just click C2, right? And then click OK, and then you would get this graph here. Now notice that for the males, we have a mode, right? 26.3 is repeated twice, but for females, there's a star there. There's no mode. There's no repeats. Okay? So, any questions about that? So all those other modes don't exist anymore because they were in different groupings, right? The other numbers that we saw. Each of those values were in different groups. So that's why they sort of disappeared. And the only one remaining was 26.3, where both of those values were in the male category. But it gives you the mean and the median and the mode for each of these groups. So Minitab will do that for you. All right, let's go back to 3.6. All right, now what do we do here? We're doing the same sort of thing. We're doing a descriptive statistics. So again, stat, basic, display descriptive statistics. And in this case here, we are simply selecting closing price. That's all we have. Right? And then we click OK, and we end up with this. Notice skewness is even bigger here, right? 0.69, bigger skewness. And you might ask, well, wait a minute. There doesn't seem to be as much of a difference between median and mean here. right, as the previous example. Why is the skewness bigger, right? The answer is because the data is more is probably more squished together here than it was in the previous example, 3.1. All right. In other words, this example here, you see a bigger difference. Well, maybe it's about the same, but the skewness is less, and that's because the data is more spread out. All right. So there's something to be said about that. All right. So let's go back to the closing price one here. There's no mode, significant skewness. Now tell me, in this particular case, is it left skewed or right skewed?
Right.
Right. It's a positive number, so it's right.
Okay, it says it's right skewed because it's positive, and yet we're seeing median bigger than the mean. So this is the point. The skewness here, this is an overall picture of the curve, overall. And sometimes there's a mismatch between the relationship between mean and median and the skewness. So even though the mean is less than the median, which would possibly indicate it being less negatively skewed, we're seeing positive skewness here. So there might be a reason for this, right? There might be a reason. There might be an unusually, the curve could be, in this case, look like this, but there could be an unusually small value in the data set that's making the mean smaller, right? Although the trim mean is even smaller. So it could be, it's probably not that. It's just there's something that's pulling the mean smaller, some values that's doing that. And yet there's also some bigger values in the data set that's making it pull to the right. That's why data is kind of messy. That's why I wanted to show you the skewness measure here, because the skewness measure should give you the overall picture of this closing price. And if we were going to do, actually, one interesting thing to do here is probably create a histogram. Maybe just let it default to its regular, hit the regular histogram without trying to figure out what the number of bins are. But if we did a quick histogram of this, simple one, and just click OK, and we'll just choose that and just let it do its thing. See what it looks like. It looks like this. And you see it tailing to the right over here, right?
Mm-hmm.
But notice that the smaller values, there's another significant piece over here, right? To the left. And this bar right here is probably responsible. This bar right here at 40 is responsible for making the mean smaller than the median. Okay? And yet, we see it tailing to the right here. There's more positive skewness than there is negative skewness on the left here. So overall, there's more positive skewness. So when you see the mean smaller than the median, yet a great deal of skewness, then you know there's something unusual going on here. And that's why making maybe a drawing of the histogram might be helpful, give you a feeling for what's going on. And now we see the reason, right? This bar here, centered at 40, is causing the distribution, the mean, to be smaller than the median, but it doesn't necessarily make the skewness negative. It's not enough to make the skewness negative. All of this here makes the skewness positive. All right. So I would go with the skewness measure as it's a formula, right? It's a formula. I would go with that to tell me whether it's positive skewed or negative skewed. Okay. That's an interesting example. That's why I picked it, because, oops, sorry. I got lost there, so let's go right back. All right. Any questions about that one? Now, in the book, they didn't ask you to check off skewness, but I think in this example here, if you didn't check off skewness and didn't make the drawing here, you would probably think that it was negatively skewed, not positively skewed, right? If you just simply compared the mean and the median, you would come to the wrong conclusion. You have to be careful with this. All right, so always make a drawing like a histogram, and that always gives you a clue about what the shape of the distribution is. All right, so let's look at 3.8. Go to same page. This is, by the way, an example. 3.8 is an example of a weighted mean. 3.8. Let's go to it. Right, that's not it. Where is it? Well, actually, there's nothing that I created for this one. I just did the calculation. So let's show data only. On this particular one, if you read through it, it says, according to a utility company, utility plant expenditures per employee were approximately, and then it gives these 5 numbers for the years 2005 through 2009. So this is 2005, 2006, 2007, 2008, and 2009. I guess I could have put a column in here for the years. And then they gave you the number of employees for each of the years. So these are the expenditures per employee and then the number of employees. If you multiply these two numbers, it should give you the total expenditures for that year. Does that make sense?
Yep.
And this is a weighted average. If you wanted to find the average total expenses, it would be a weighted average, where the values in the data set are these 5 expense numbers, and the weights are the number of employees. Now, I created 2 columns here because I wanted you to see the difference between the weighted average and the mean expenses. The mean expenses would be what? Would be simply the average of the arithmetic average of these 5 numbers.
Mm-hmm.
That's where the 49,424.60 comes from. This 49,370.7 comes from what? It comes from a weighted average. So let me show you how I came up with it using the calculator. I'm going to go back to C4. It'll remember what we did in C4 if you just hit enter here. Oops. Sorry. I didn't want to hit enter. Oh, here we go. C4. It doesn't remember what I did. Oh, maybe I didn't click assign as a formula. Now, how did I come up with the weighted average? Now, I want to multiply each of these each set of 2 numbers here, right? There's 5 of them. I want to multiply the expense times the number of employees for each of these years. I want to add up those products, and I want to divide by the sum of the employees. Does that make sense?
Mm-hmm.
So in the numerator, I'm going to pick a sum. I'm going to paste sum. Now it says sum rows, but I don't want to. I think that's used if you wanted to sum only particular rows in a data set. But if you want to sum all of them, just pick sum. What did I forget here? I don't think I forgot anything, so I said pick sum. And select. Oh, there we go. Now, what am I going to put in the middle here? I'm summing what? I'm summing the product of C1 times C2, right?
Mm-hmm.
Expenses times the number of employees. This is the X, this is the weight. So it's going to be, so in here, I'm going to say C1. And then I'm going to say times C2. So that's my numerator, the sum of those products. And then I'm going to divide that by the sum of the weights, the sum of the number of employees, which is C2. So I'm going to say sum again. And in here, I'm simply going to put C2, or I'm going to choose it, C2. And this is the weighted average formula. Does that make sense?
Mm-hmm.
Numerator is the sum of the product of the number times its weight, divided by what? The sum of the weights. Right. I click that, I click OK, and I should get that 49,000. Whoops. Yeah, 49,370 as the weighted average. In C5, this is simply the mean. And of course, you could, if you want. I think they have the mean here. I think. Let me see if they do. Right, the mean. You simply go mean. C5. So I'm going to change this to C5. And then this would simply be the mean of expenses. Now then there's not much of a difference here, and the reason why is because these weights here are not that far apart, right? There's not a huge difference between them.
Right.
So there's some difference, but not a significant difference. But that's how you do it in Minitab. All right. The Minitab doesn't do a weighted average. It doesn't have a weighted average. So you have to do it yourself with a formula. The mean, of course, you could simply, you could have simply gone here, right, and gone to the basis of statistics, right, and simply picked expenses. And in statistics, you just check the mean, right, and uncheck everything else, and it'll give you your answer. Any questions about that? How to do a weighted average? It's pretty straightforward. And then the last thing, we're almost done, is 312. This is a data set. Now this one I actually, this is on same page 67. This data set's called XR02, so this is chapter 2 again, 067, and I posted that in this week's module. So that data set's posted. So this is what it looks like. Let me read through what this is supposed to be. It says for the U.S. News and World Report, top 50 U.S. law schools, find the mean and median scores that the schools receive from academic evaluators. So these are scores from for the academic ones, I guess from 0 to 5, or 1 to 5, I don't know, 0 to 5, I guess. And these are just ratings that academic people are using to evaluate these law schools. So, and then you have also another group here called lawyers and judges who evaluate law schools. So academics, probably professors of law schools, who are evaluating the top 50 law schools, and then there's people who are actually working in the legal field, lawyers and judges, who are also ranking these same 50. All right. So anyway, they want you to compare the mean and median scores for both the academic group and the lawyers and the judge group. They want you to see if there's any skewness to these two groups. All right, so again, mean and median, that's all we're going to be looking at, the mean and median. And I would also do skewness, right? I would have the skewness, I would check that. They don't mention that here, but I would definitely check that. And so again, I would do basic statistics. All right. And I would do one for each one of these, right? I would choose both variables. So, oops, I already chose both variables. So choose both of them, put them in variables. And then for statistics, again, mean, the median, and skewness. No harm with the count here. It doesn't, not harmful to do that. And then I ended up with it automatically layers it like this for you. If you choose 2, it'll give you the whatever you choose for descriptive statistics for both of those variables. Now notice in both cases, the mean is bigger than the median. And notice that the skewness is bigger than for the academic ones than for the law and judges ones. But they both show positive skewness are the skewness values. And the mean being bigger than median is also consistent with it. Okay?
Mm-hmm.
And again, you could confirm this by doing histograms for both groups. And then you'll probably see, you can see the positive skewness in both groups. So the answer is, do either of them show positively skewed or negatively skewed? The answer is they both show positive skewness, but a little more skewness, positive skewness, in the academic group versus the law and judges group. Mean is and actually the mean is bigger in the law and judges group, right? The mean and median are bigger, but the difference between these two is not as much. It might be useful to actually take a look at the histogram for both. So yes, I could choose with groups, right? Let's try it. Why not? And then the graph variable again is what? What are we going to choose here for our value? Read through it here. Mean and median scores. So let's just choose both of these as graph variables, right? There's no really categorical variables here. So I'll choose both of them. Let's see what happens. I'm curious. See what we end up with. The academic group, here's the academic group here. And here's the law and judges group. So you could see that the mean it does look bigger for the law and judges group, and probably the median the same. But the skewness is bigger, it's more for the academic group, right? Can you see it or maybe not? Maybe we should create 2 of these instead of, not as clear with this. Let's try it with them as separate. We'll do simple ones for each one. Here's the academic one. Okay. All right, and let's look at the other one. This is the larger skewness. And then let's do another one. Another histogram for the other one. And it's hard to say, hard to see it. I think the reason why this one doesn't have as much skewness is because of these two bars right here. See that?
Mm-hmm.
If it was really tailing off, it would not be, because look at the other one. Tails off more, right? Would you agree? More tailing off on this one here?
Yeah.
And this one, not as much tailing off because of these two bars here. So that's why the skewness is less here. All right, so these histograms are helpful, aren't they? They do give you an idea of why you get the skewness values as you do. All right, that's it for tonight. Any questions about this? I mean, was this useful, helpful? Yes?
Professor, I got a question.
Yeah.
Um, are you saying the skew distribution has the similar curves as the histograms?
Histograms are giving you a way of looking at the shape of the distribution. So both, in this case here, in both of these cases, I hope you can see that there is the most of the distributions to the left here. You see it?
Mm-hmm.
And then there's a drop off, right? It's
Mm-hmm.
not perfect, but you can see it drops off. The frequencies drop off as you go to the right.
Yeah.
So you could picture drawing a curve like this, you know, drawing going up and then drawing down like this. It's definitely tailing to the right.
Okay.
So this helps you sort of visualize it. That's all I'm saying. It's helping you visualize what the number is saying. The number is saying positive skewness. And these numbers here, these larger values out over here, are pulling the average to be big, or the mean to be bigger than the median. All right? So the mean is somewhere out here, and the median is over here somewhere. Okay?
Yeah.
This one also shows something similar, except it's not as nice. You know, you can see most of the curves to the left here, and then when it tails off, it sort of gives you a second little bump here before it goes back down. This little bit of these two bars here, you didn't see that as much over here. You see it? This one has a little bit of an increase here before it goes back down. These two bars, it decreased the skewness to, all right, because of there's more data values right in these two bars here. So it's still positively skewed, but because of these two bars, the amount of positive skewness is not as much. And that's why we get more skewness in the academic group than in the law judges group. You can see the numbers here showing it. So the histograms are trying to explain why, that's all.
Okay.
And I think the purpose of this course is to give you a way of intuitively looking at data and trying to figure it out, you know, by looking at things like the histogram or a dot plot. You can do dot plots too, right? Dot plots also, you could probably see the same type of thing. Okay. Did I answer your question, Han?
Yeah. Thank you.
You're welcome. All right. And Mo, are you okay too?
Yes. Sorry about my camera. I think some crayon wax might have melted in front of it.
Oh, okay.
Because sunlight's still coming through, like when I move my hand, but whenever I turn it on, it's just not showing my face. I had it in my bag with some crayons for like my little cousins, and I think that it broke.
Oh no. Oh. I keep all my old, like my grandchildren, I keep them away from my stuff so they don't break it. All right. Well, I know you're there. I hear you. So, and you're sort of a shadowy figure tonight, but that's okay.
Sorry.
That's okay. All right. So, if there's no questions, remember, if you can get the homework to me by Thursday, the homework that I assigned over the weekend, just send me an email with your answers, and then we'll continue in this chapter talking about dispersion next time. the different measures of dispersion, and then we'll do, again, some examples just like what we did today. All right? Sounds
Okay.
good?
Yep.
I know it's kind of late, but if, unless you have any, do you have any other questions?
No.
No? All right. Great. I will see you on Thursday. And
All right.
Thursday, it's
Yeah.
going to be a little earlier, 7:45.
Right.
Thanks,
All right.
Professor.
Yes. Okay, good. All right. See you later.
See ya.
Yeah.
All right. Bye-bye.
Bye.
Bye.